Thank you, Chair, for the introduction. I'm Fujiwara from Universidade of Campinas, Brazil, and today we'll talk about a biocompatible artificial skin with an embedded optical fiber specklegram sensor. So this is the outline of my presentation, but let's move to the introduction. Tactile device achieve information about force, texture, and shape by the physical contact between the sensor and the environment, and they have several applications, including user-computer interface and optical device, robotics, and so on. And a special type of tactile sensor are the artificial skins that imitate the characteristics of the human skin, and they are comprised of a sensing layer over a perception layer with several mechanical receptors to detect the distributed information about pressure, sleep, vibration, and also chemical stimuli. And actually, there are several types of transducers available for this purpose, such as resistive, capacitive, piezoelectric sensors, and also optical ones. But the problem is how to achieve a flexible design and also ensure distributed measurements by minimizing the number of sensing elements, making it more compact and with less channels to access. So one option to solve this problem is using optical fiber sensor, because they are intrinsically lightweight, flexible, and can resolve the special information along the fiber. There are some examples of fiber sensors for this purpose, for example, FBG and also microfibers embedded in flexible substrates, such as polymers and so on. But the problem is still the question of reducing the number of channels, I mean the number of fibers and wavelengths that we have to detect to retrieve the special information. And it also relies on expensive instrumentation such as a tunable light source and also a spectral analyzer. So to solve these problems, in this paper, I propose an optical fiber artificial skin tactile sensor by using biocompatible and biodegradable gel made of agar. Okay? And then I process the output light by using the specklegram analysis to achieve a high sensitivity and also ensure a low-cost interrogation step with a single measurement channel. So talking about agar, agar is a gel-like substance obtained from red algae, and it has some interesting characteristics. For example, agar is edible, is flexible, transparent, and it's also moldable and thermoreversible. And we can also tailor the optical and mechanical properties of the agar, for example, the refractive index and the viscoelasticity of the gel by changing its composition. And we previously designed in cooperation with Universidade in Japan some optical device made of agar, for example, lenses, lenses and reflectors and spheres, and also structured optical fibers like this. Okay, we also designed some types of tactile sensors by using agar. For example, this bulk pad that detects a force applied on the fiber with embedded fiber here. And we also designed a skin whisker-like structure that detects the direction and the magnitude of the bending in the whisker tip. So we evolved this concept to a more compact design, which is an artificial skin, which is this concept here. So how to fabricate this kind of sensor? It's like cooking, okay? We can just take a mixture of agar and glycerol and water, then we heat it, and we pour the solution, heated solution, in a mold containing the fiber. And after the solidification, we can remove it from the mold and obtain artificial skin like this, okay, with very transparent design, flexible too. And we can embed the sensing fiber inside the agar substrate. In this case, we achieved 2 millimeters of thickness of this structure. And the sensing fiber here is a concatenated multi-mode, single-mode, multi-mode fiber structure, because we'd like to take part of the light from the core modes, from the launching fiber here, from the launching multi-mode fiber, and then couple it to the cladding section of the single mode fiber, and it will interact with the environment and will take the physical and chemical information, and then part of the light will couple to the output multi-mode fiber here. And as we have a multi-mode fiber, we will obtain a speckle pattern at the fiber output like this, produced by the interference between the several modes in the mode fiber section. And this the speckle pattern is sensitive to any kind of physical or chemical stimuli applied to the fiber, so it's changed by mode coupling and phase deviation effects. And even though it's a problem for example, optical communication systems, because it's very sensitive to any kind of disturbance, actually speckles contain a precise and reproducible information about the fiber state. So we can decode the information inside the speckle pattern and obtain the magnitude and the position of the stimuli applied to the optical fiber. Okay, so So the experimental setup is basically visible laser, helium neon laser that illuminates the fiber, and then we apply a stimulus U at the position XD over the tactile sensor surface, and then we detect the output specklegram by using a CCD camera and process it by a MATLAB application. So this speckle pattern is firstly filtered, then converted to the grayscale, and then we compare the current speckle pattern to a reference condition one by using a correlation function. In this case, we use the zero mean normalized cross correlation coefficient that compares the actual speckle pattern to the reference one here. And when the image deviates from the reference IR, then the Z value decreases, and then we can take this value to predict the magnitude of the applied force, for example. And furthermore, we can set different types of reference to each position along the fiber, because if we press the fiber, for example, here or here, then we will obtain different speckle patterns, and then we can calculate the ZNCC for this reference and for another reference, and then decode the position of the force applied on the fiber. So we can detect both the magnitude and the location of the applied variable. So let's move to the results. Firstly, we applied a crescent force in a single position of the artificial skin here. And we can see that as we increase the force, the speckle pattern changes, and then we can calculate the correlation coefficient. And then by taking this value, we can predict the applied force. Assuming this linear region here from 0 to 0.2 newtons, we can take this maximum deviation here and estimate a force resolution of 0.03 newtons, which is a good value for a tactile sensor. Regarding the spatial response, we use a constant force of 0.1 newton, and then we change the applied force along several positions on the fiber, and we compute the ZNCC for the neutral condition without any force, and for the condition with a maximum force at the center. And we can observe that as the position of the force shifts from the center, this ZC value decreases, and then we can take the location of the force by decoding this curve. And by taking this linear region here, we can estimate resolution of 0.7 millimeters. And of course, we can improve the result by taking more reference spectrograms and calculating the correlation to remove the ambiguities in the estimation of the position. Okay. Talking about dynamic response, then we apply the SAP stimulus in the tactile sensor, and then we observe its response here, take the time constant, and we observed 0.04 seconds of delay response. But actually, you can also change this value by tuning the gel, for example, by adding more glycerol to make this more rigid, or adding more agar to make this more viscous. So we can make this response be more delayed or faster according to the gel composition. And we also measure the bending. It's just show that the artificial skin is foldable, and we can detect the bending resolution with 0.14 degrees. Okay. As you can see here, after some certain value, the ZNCC metric tends to saturate, but we can actually use an extended version of this metric to achieve a very linear response along the whole measurement range. So it's possible to circumvent this saturation problem here by using another algorithm. So we also tested its response to the temperature. and for example, between 30 degrees here, and we can see that the speckle pattern also changes by heating the tactile matrix, and we achieved 0.3 degrees Celsius of resolution. Of course, we cannot apply at very high temperature because the agar will melt, but this response is suitable, for example, for measuring the body temperature, and also the agar gel can endure at room temperature at normal conditions, so it's very durable too. And finally, we tested the sensor response by, for example, dripping droplet of water on it and then observe how the optical signal changes. And we can observe that as the agar absorbs the water by swelling effect, then it will make the gel inflate, and it will also press the fiber. So we can see that by adding liquids, the optical response also changes. So we can change the liquid and try to decipher which is the fluid applied to the optical sensor. And by also breathing close to the tactile sensor, we can observe that it can also retrieve the cycles of respiration too, the inhaling and exhaling cycles. And then we can use it also as a biomedical sensor for respiration measurements. So in conclusion, in this work, we propose another tactile sensor, okay, using specklegram analysis, and we measure force, temperature, bending, temperature, and also we demonstrate how to measure chemical variables. And in the future, we would like to improve the sensor by also tuning the gel properties and try to use it in biomedical applications. And just a final comment, we are also trying to remove the silica and make a now biodegradable tactile device. Is the very first version of it. It's still a bit bulky, okay, but we like to make it more thin. But the idea is to create a light guiding structure inside the agar gel. Then it can be used as a sensor, and then it can be absorbed by the organism after its use. So we don't need to use a silica fiber to detect the light. Okay, so that's it. Thank you very much.